Okay, apparently I didn't hit the record button this morning, so no. Good catch. Thank you. All right.
The difference is, isn't displacement like the change of position, and then the distance is just the magnitude of that?
That's right. What do you mean by magnitude, Amber? That term magnitude is going to get thrown around a lot in physics.
Like it ignores the direction it's going just as a...
That's exactly it. So when I talk about something's displacement, I'm talking about, the change in its position. So if I'm looking at what did I just do? Sorry. There we go. So if, let's say this guy over here traveled to talk with this guy over here, he would be going from x equals 3 to x equals 5. So his displacement would be his change in position. And to go from 3 to 5, you have to change by 2, right? So displacement, mathematically, is just delta x is your final position minus your initial position. Distance, however, is distinct from that because distance is only about the magnitude, the numbery part. And the reason that matters is because if this guy goes from here to here, he's moving in the positive direction. His displacement is positive 2, or 2 meters to the right. And displacement is an example of a vector where, to talk about the displacement, I have to have both pieces of information, both how far it moved and also what direction. Distance, however, does not care about what direction you're traveling. It's like the odometer in your car. Whether you're driving north or south, the number of miles on your car are ticking up. They never go back down when you turn around and go home. And so that means that if you're tracking those things, you want to pay attention to that. If this guy starts at x equals 3, travels from here to here to here and back, his displacement over that entire trip is 0 because he both began and ended at the same location. The distance he traveled, however, is not 0. He went 2 meters this way, then he went 7 meters this way, then he went another 5 meters this way, and I'd add all those up, and that's his distance traveled. So you had to know that distinction, and which one of these is important to us depends on context. So that was the second thing that we learned, was how to differentiate between those two values. Hopefully this is all pretty straightforward, because this is back when things were easy. The next thing we learned was velocity. Right, and we defined velocity as just the rate of change of the position. Well, notice the change of position, that's the displacement. And if I take the rate, it's always whatever your change is per something, in this case, per time. And that was the velocity of an object. By contrast, a related term, speed, is just the magnitude of that change. Which means if I ask you what the speed of an object is, I don't care what direction it's moving. If I ask you the velocity of an object, I have to have both pieces of information, both the speed and also its direction. So, be on the lookout for that sort of thing. Very often I will phrase questions in such a way that I'm choosing my words very carefully. And if I ask you what's the speed of this object or what's the velocity of this object, the answers might be slightly different. If I have an object that's traveling to the right at 5 meters per second, its velocity is 5 meters per second to the right. If I ask you for the speed, it's just 5 meters per second. If I say I have an object that's traveling with a constant speed, it means that it's traveling at a constant speed, but the direction might be changing. So I could be driving around in some weird, snaky path, As long as my speedometer says 5 the whole time, that's a constant speed. But if I'm driving with a constant velocity, that means something different. That means that my speed is staying the same, but also the direction I'm traveling is staying the same. So if I have a constant velocity, I'm traveling at one speed, and I'm also traveling in a straight line. I'm not turning at all. So be aware of that distinction because it can be important. The last thing we learned back in chapter 2 was the acceleration. And just like velocity was the rate of change of position over time, the acceleration was the rate of change of velocity over time. Right? So you have an acceleration if your velocity is changing from moment to moment. Now, the most common thing that I see students screw up, usually what happens is, 6-7 weeks into the class, we moved on to other topics, and we're in the middle of lecture, and I'll call on a person and ask, hey, Stephen, what's the definition of velocity? And frequently what will happen is Stephen's response will be velocity over time. And that's slightly incorrect. Why is it incorrect?
Why is what incorrect?
The question I just asked. So if I call a person out and say, hey, what's the definition of velocity or acceleration? And they respond, it's velocity over time. That's not correct. Why is it not correct?
Because of the change of velocity over time?
It's not the velocity, it's the change in velocity. So what sometimes people do is in their heads, they kind of, they translate this all down into like its simplest way of remembering, and that's how they remember it. They think of velocity as distance over time, but it's really displacement over change in position over time. And distinction is sometimes going to be important. Because if I tell you I have an object that travels with a speed of 5 meters per second for 2 seconds, what's its acceleration?
Wait, so the acceleration is the
change in velocity over time.
change of the position, like the rate
No,
of change of position.
Acceleration is change in velocity over time.
But velocity is the change of position over time.
That's a true statement, yes. But if I say I have an object that travels at 5 meters per second for 2 seconds, what is the acceleration? What would you tell me?
Wouldn't it just be 5 divided by 2?
Nope. And that's why I'm bringing this is why I'm making that point, because that's a very common mistake, Brittany. Because it's not 5 divided by 2, because think through the question again. I said it's traveling 5 meters per second for 2 seconds. So at the beginning of that 2 seconds,
So
how
5
fast is it going?
Because if you're 5 meters per second and you only travel for 2 seconds, that's
Mhm.
10.
Well, if I'm going 5 meters per second and I go for 2 seconds, I will travel a distance of 10 meters. That's true, but that's not what I asked. So you're not wrong. You're just answering a different question than the one that I'm asking. But what's going to happen is if I have an object that's traveling at a velocity of 5 meters per second, and it travels for 2 seconds, then here's my object, here's my dude. So when I first start my timer, when I start my stopwatch at 0 seconds, how fast is the dude going? He's going at a speed of 5. Now, 1 second later, he'll be over here somewhere. What's his speed when he's here? 5. 1 second after that, 2 seconds. What's his speed over here? 5. Because if all I tell you is that he's traveling at a speed of 5, and he does it for 2 seconds, his speed, his velocity is not changing. He's traveling a constant speed in a straight line. So if I ask you his acceleration, it's not 5 over 2 because it's not v over t, it's delta v over t. And so his acceleration is going to be his final velocity, his velocity at the end of that 2 seconds, which was 5, minus his original velocity, which is at the beginning of the 2 seconds, also 5, which means his acceleration was 0. And so that's the sort of mistake that I see people make all the time. And it's important to be aware of that, right? If I just tell you like one velocity at a time, that does not give you an acceleration, because to have an acceleration, your velocity has to change. It has to go from being 5 to being something else. Now, if I told you that the guy started at rest and moved for 2 seconds, and at the end of that 2 seconds, he was traveling a velocity of 5, then the answer would have been 2.5, because then he would have started at 0. He would have had some in-between speed here after 1 second, and then at the end, he would have had a speed of 5, right? But in that case, he would have been speeding up the entire time. So when you're reading questions, it's important that you break it down like that. It's important that you think and ask yourself, does this object have a velocity that changes as time goes on? Because if it's not changing, your acceleration is 0. So, we learned in Chapter 2 a gazillion ways of thinking through all of these things, and they could all get boiled down to a whopping 4 different equations. We call them our 4 kinematic equations. And they were pretty easy. Officially, they don't have names, but I always give them names because it makes it easier for me to talk about them with my students. Let's call this one the position equation. I always call this one the velocity equation. And if I wanted to sound hoity-toity and snooty, I'd call this one the time-independent velocity equation or something like that. But for me, every time I see this equation, it always makes me think of that problem where I'm trying to stop before I run over the deer. And so I always call this stopping distance equation. Again, it's not an official name, it's just kind of how I think of it. And then this one here, I hardly ever use, because a lot of times I'll end up solving things in a way that avoids it. So I always call that one the useless equation. It's not really useless, but I feel like it is sometimes. So those are the 4 equations of motion that we started with back in Chapter 2. And the thing about each of these 4 equations is that if you're dealing with a Chapter 2 problem, there's really only 6 things you're keeping track of, right? Where the object started, where it finished, how fast it was going originally, how fast it was going at the end, the acceleration, and the time. Those are the only 6 things we're ever tracking in a kinematics problem. And the cool part is that each one of these equations is missing a particular variable. And that is going to be kind of a signpost to help you figure out when it is appropriate to try and use that equation to figure out whatever it is you're trying to figure out. So the missing element from this position equation is that nowhere in the position equation does the final velocity appear. The missing element from this equation is it contains no x's, nothing about the position or where the object is. The missing element from this equation is time. There, I don't really care how much time has elapsed. And the missing element from this equation is the acceleration. And so what's going to happen is when you're solving problems in the context of Chapter 2, the basic process is always the same, right? The first thing you need to do is get a physical sense of what the heck is happening. I almost always start with a diagram. And the reason that's important, this is probably the most important part of the entire problem, is that if an object's moving around, you have to make sure you can sort of visualize what's happening and be able to piece together what pieces of information given in the problem apply where in your diagram. So you're going to label the heck out of that. I suggest, as you're making your diagram, maybe I've got an object and he's like, okay, my guy starts over here, and then I know that he travels, let's say 5 meters, and 3 seconds later, he's here, right? So, maybe I know, when he's here, he's got a velocity of 0, right? So what I'm doing is I'm just keeping track of what things I know about that scenario, and I'm trying to use the picture as a way of augmenting my working memory, right? I can't keep all the numbers straight in my head, so by diagramming them, it's like, this number 5 that appears in my question, what does that mean? Oh yeah, that's how far it is from here to here. I can look at my picture and it's obvious what it means. And most of the physics happens in you guys making those associations. If you guys try to jump straight to the equations, you're going to start plugging numbers into places they don't belong because you don't know what the numbers stand for. So don't try to jump straight to the equations and start chugging numbers. That is a recipe for disaster, particularly on the more complicated problems. If you start with this diagram and you label it through the way that I've tried to teach you to do, you're going to find that a lot of these problems are way easier because it's going to be easier to see how to approach them. So the whole point there is just to try to get a sense of the problem with that diagram. Now, the second thing that I tend to do is now I need to do the kinematics. I need to describe the scene that I've drawn out. This means I have to choose a coordinate system. And take inventory of all the information that I've amassed. Right? And the thing is, in a chapter 2 problem, there's only 6 things in that inventory, right? I usually just make a list. There's my 6 things. And of those 6 things, which of those do I know and which ones do I not know? Right? So once you've filled in those blanks, here I said, this is my starting point, that's my ending point. I'm going to go ahead and call this location x equals 0. And that means that this other location, which is 5 meters away, that must be x equals 5. So I've chosen where to call 0. I picked this spot. And then I've numbered any other location relative to that spot. That gave me my final position. I said, when he's here, he's got a velocity of 0. So my starting velocity, that's 0. My ending velocity, I don't know. Nobody said anything. So I don't know how fast he's traveling then. I also don't know, when he gets here, what his acceleration is, because nobody told me. I do, however, know that from here to here, 3 seconds have passed. So there's my inventory. And the reason this step is important is because very frequently I get students who are like, I don't know how to use what equation. When do I use this equation? When do I use this other equation? And in these kinds of problems, looking at that inventory is going to tell me what equation will help me. So 3, what I'm going to do is pick equations that avoid unknowns that you don't care about. Right? So let's say that the question here, maybe I want to know what's the acceleration of the guy, right? I know he went from here to here. He took 3 seconds, but I don't know what the acceleration is, and I don't know how fast he's traveling. So there are 2 things I don't know. But the question maybe didn't ask me how fast he's traveling. It asked me about this. So, if that is the case, looking at that inventory, I need to have an equation, and it has to include acceleration. So, that means it can't be the useless equation because the thing that I'm looking for doesn't appear in that equation. This equation is no help at all. However, this equation doesn't have the final velocity in it, which is good because I don't know it. If I picked this equation or this equation, I'd run into an issue because both the acceleration and the velocity, two things that I don't know, both appear in the equation, and I couldn't solve it. So by looking at the inventory in this way, it's pointing to me saying, hey, pick the one that doesn't have this. Which one doesn't have this? This one? Boom, there's my equation. And then step 4 is solve it. Right? Once I get to step 4, it turns into a math problem. Right? All the physics happens in these first 3 steps. Everything after that is just doing some algebra to figure out whatever it is that I'm missing. So that was the basic topic of the second chapter. In the third chapter, what changed? We started talking about things in 2 dimensions. So maybe I've got a dude, and that dude is throwing a baseball, and later on the baseball is here, and it's traveling horizontally at that exact moment with a speed of 5 meters per second. And maybe it's at a height of, I don't know, 10 meters. He must have thrown it with some starting velocity and at some starting angle, but I don't necessarily know what those are. Right? So all that's happening here is my starting diagram is more complicated because when I'm tracking the positions of the object, I have to worry about how far sideways it's moved and also how far up and down it is. But it's the same basic process, right? The difference being that of those 6 things that I'm keeping track of, and a lot of times what we'll do is in 2 dimensions, I like to even reserve X for just the sideways stuff and Y for just the up and down stuff. So instead of calling the position X, sometimes what we'll do is we'll call it R. So R is just a position vector, and R is going to have components of whatever X is and whatever Y is. And each of these first 6 things are vector quantities. And all we've got to do is break them down as vector quantities. So what's going to happen is each one of these things is going to have something I hat plus something j hat. Except for time, because time is a scalar and therefore does not have a direction associated with it. And so what we'll end up doing is breaking all of these vectors down into their components. And then we'll fill in an inventory. And the cool part is that what's going to happen is the same 4 equations are going to work, except now they'll be able to work both in the x direction or in the y direction. So we've got twice as many equations and almost twice as many variables. It's a bit more messy, but the process is basically the same. You do the inventory, figure out what you know, and then you look for ways to figure out the missing pieces by finding equations that include the stuff you do know and also include the stuff you want to know, but avoid anything that you don't already know. So chapter 3 is very similar to chapter 2 in that regard. Now, the big process here is, how do I break these things down to begin with? How does that work? And that's a process that became important in chapter 3, and it stuck around for chapters 4, 5, 6, and 8. And I guess also 9 and 10. So almost every chapter except for chapter 7, we had to deal with vectors and how to break vectors into components. Next semester, when we come back for Physics 2, we're going to have to break down vectors then too. So it's the most important thing you learn in this class. is how do I do vectors? How do I break down a vector?
I have a question.
Yeah.
Oh wait, never mind.
Okay, no answers. So let's imagine that I've got an object, and maybe that object is traveling with a velocity of 10 meters per second, but it's doing so in some weird, annoying diagonal direction. Maybe it's traveling 60 degrees above the horizontal. So what I'd like to do is I'd like to express that vector, and I've represented the vector visually by drawing an arrow in the direction of the velocity and having the length of the arrow be scaled with how big the velocity is. That's the magnitude of the velocity. But I'd like to be able to express that in vector notation. So how do I do that? How do I break that vector down into vector notation? Well, the trick is, I imagine that this vector is itself the sum of two additional vectors. This would be what I call the x component, and this is what I would call the y component. Notice that I've drawn arrows for both of them, and I've put those arrows tail to tip, because conceptually, when you add vectors together, you're putting them tail to tip, and the sum of those vectors is the vector that goes from the tail of the first vector to the tip of the very last vector. So what I'm effectively saying by drawing it this way is that this x component plus this y component must add up together and be equivalent to this annoying diagonal vector. And by breaking it down into those components, it's going to make life easier for me when I go to add this vector or do other math operations on this vector. Doing it in diagonal form is irritating and difficult. Doing it in component form is super easy. And we like to break the problems down and make them be easy. So how would I do that? Sines and cosines. I remember from pre-algebra that if I have a right triangle, the sine, cosine, and tangent are the ratios of sides of that triangle. And in this case, I know that the purple side has a length of 10 meters per second. That would be the longest, or the hypotenuse, so I know all the h's here. And what I'm looking for are either the x or the y component. And if this is the angle that I'm referencing, this part right here is adjacent to that 60 degrees. So the x component in this case would be my adjacent component. And the y component doesn't touch that 60-degree angle. It would be my opposite component. So if I'm looking to find how big those sides are, I can exploit those ratios. I know that the sine of that 60-degree angle has to be the ratio of the opposite side, which is the y component, over the hypotenuse, which in this case is the full 10. So if I want to know what the y component is, I'll just solve for that by multiplying both sides by 10. Then I get 10 times the sine of 60 is the y component. And of course, what's the sine of 60? It's the square root of 3 over 2, which is like 0.866. So if I multiply that by 10, it's like 8.66 meters per second. That's my y component. Meanwhile, I can do the same trick to figure out the x component, because if I haven't used the cosine yet, I can now. The cosine of 60 is going to be the adjacent part. That's the x component, still over the hypotenuse of 10, which implies that the x component is just 10 times the cosine of 60. Cosine of 60 is 1/2, and 1/2 times 10 is 5. So I found that component. Super easy. So now if this were, say, my starting velocity for this problem over here, I could say that v initial is going to equal 5 I hat and 8.66 j hat. I've written my vector in vector notation. Now, a common mistake that I see students make is students will invariably start to associate x with cosine and y with sine. And so sometimes they'll get a problem where they have to break things down into components, and as a knee jerk, that's what they'll do. And I'm a jerk, I'm tricky. A lot of times what I'll do is I'll put in problems where if that's the way you think, you'll get stuff wrong, right? How would that happen? Well, what if I had a vector and I told you that this vector was, let's say, down and to the left, 10 units long. I tell you that it's not quite straight down, but instead it makes a 10-degree angle with the vertical. If I wanted to write this vector, let's call this vector A. If I wanted to write vector A in vector notation, I'd have to break that down into components. So I would imagine that I'm getting this vector by drawing one component that's in the y direction only, another component that's in the x direction only, so this is my y part, that's my x part. And I go to break that down. And I know that I'm going to use sine and cosine both, so I'll start with the sine of 10 degrees. But when I do that, the sine is the opposite side over the hypotenuse, and the opposite side of the triangle is not the y part, it's the x part over the hypotenuse, which is still 10. So you'll notice that here's an example where I'm getting the x component, but I'm getting it from the sine. And it all has to do with which angle I've got. By the same reasoning, the cosine of 10 would be the y part. So if I were to write vector A in vector notation, I could say that it's 10 times the sine of 10, whatever the heck that number is, I can't do that in my head, in the I hat direction, plus 10 times the cosine of 10 in the j hat direction, except, oh wait, even that's not correct. Where did I screw up? We don't know. We fell asleep 5 minutes ago, Fleming. So, you'll notice this vector points down and to the left. Typically, I choose coordinate systems, unless I have a compelling reason not to, which are standard Cartesian coordinate systems, where x is in the positive area is to the right, and y is going up. And so what that means is that it's pointing in the negative x direction and the negative y direction. So in order to make this truly correct, what I would want to do is to denote those directions with my choice of signs. It's not going to be this I hat, it's going to be negative that I hat. It's not going to be this, it's going to be negative this.
So this is the one where you can pick your coordinate system? Or
Yeah, you could always pick your coordinate system, right? But you always want to make sure you have done so. And so, like, if I wanted to, and I wanted to avoid minus signs, like maybe I'm doing a problem where I'm adding this vector to another vector that's like this, right? And the thing I'm looking at is like, man, this guy is left, this guy's left, this guy's down, this guy's down. If I pick this coordinate system, everything's got minus signs, and that's a whole lot of minus signs. So if I saw something like that, what I might do is say, you know what? Screw this coordinate system. This coordinate system is terrible. Instead, I'll choose the positive y direction to be down and the positive x direction to be left. I'm free to do that because you can pick whatever coordinate system you want. But if I did it that way, then what would happen is I would make both of these guys be positive again. So it matters what coordinate system you pick. And What would screw you up, though, is that if I wrote this like that, and then I had some other vector later on in the problem that was like this, if I'm choosing this as my coordinate system, this guy is going to have all positives, but this guy would have had all negatives, right? No matter what you pick, this vector and this vector are going to have opposite signs, because one is down and to the left, the other is up and to the right. So as long as you're consistent, you'll get the right answer. At the end of the day, if I chose this coordinate system and I did a bunch of math and my answer ended up being negative in the x direction, well, that means it's going to the left. If I chose my original coordinate system, then I would have gotten the opposite sign but the same number, but it would still mean, like if I get a negative answer for this, that means it's to the left. So both people would agree that it's to the left. They would disagree about whether to call left positive or negative. But at the end of the day, you can always choose your coordinate system. Just make sure that you know what you're choosing. I usually will make a reminder of to myself by drawing this out so that when I get midway through the problem, I stay consistent. Once I make a choice, I stick with that choice. So that was a concept that was introduced back in chapter 3, but it has stayed with us for every other part of this exam, or this course, because breaking vectors into components is something we had to do over and over and over again. You had to do it when you had momentum problems, where you had objects moving in weird diagonal directions, so it would have a little momentum in the x direction and a little momentum in the y direction. You had to do it back in chapters 4, 5, and 6, where you were doing free body diagrams, and all of those forces were vectors, and you had to break those forces into x and y components, because when you used Newton's second law, you were adding vectors, and you had to add vectors by component-wise. So how do you add a vector? I didn't try this one very well. Let's imagine that I've got 3i hat plus 4j hat, and I want to add that to 2i hat minus 2j hat. What's the magnitude and direction of my final answer?
Is this just adding it up?
To a point. When you have vectors in vector notation, and you've broken them down the way we were just talking about, adding them is easy. Because what's going to happen is, if I have a vector that's in the x direction, and another vector that's in the x direction, when you add them, you draw them tail to tip, and the sum is going to be a vector going from the tail of the first to the tip of the last. So, boom. And what's going to happen is, if this distance was 5, and this distance was 3, then it's pretty obvious, just looking at the picture, that this distance here is 8. So vectors that are along the same line, adding them is just like regular math. If you have 5 and 3, but they're not along the same line, then they add to this, and this will not be equal to 8. That's more complicated. So instead what you do is you break these vectors up. You say I have 5 plus just this part of that vector, which is the I hat component of that 3 long vector, and then that would be my total x component. And that's what we're doing over here, is we're breaking these into components and adding the components separately. So for that, it's super easy. 3 plus 2 is 5. My final answer is going to have a y component, or excuse me, an x component of 5. Over here, my 2 j's, I have 4 and negative 2. That's a whopping total of 2. So if I add those 2 vectors, that's what I end up with. But the question I asked was not, what's my final vector? The question I asked was, what's the magnitude and direction of that final vector? So how would I figure that out?
You will use that equation, but I have a question about the top.
Okay.
The 5 arrow and then the 3 arrow. Like, what is that like?
So I'm just giving you an example of if I'm adding 2 vectors that are in the same direction, it's just like regular math, right? If 5 is along the x direction, so this is 5i hat and this is 3i hat. Well, 5i hat plus 3i hat is obviously 8i hat. That's
Where
why
are
we
you
can get
getting
away
that
with.
3 from?
It was just a random example. I literally just made the two numbers up to say, hey, if I'm adding two vectors that are collinear, here's an example vector, here's another example vector. When you add them, you put them tail to tip, and the sum of two vectors is the arrow that goes from the tail to the first and the tip of the last. If I do that, it's just like regular math. That was the point. So the 3 was made up. It was part of the example. So, once I've got to here, how do I find the magnitude and the direction of that final answer?
It's the 2 formulas you gave us.
Yeah, could you be more specific?
I'm trying to find.
In a way, it's not really that I gave you a formula. In actuality, it's just you're using math you already knew. So I didn't teach you any formulas. These are formulas you guys already knew from back in the day. So to see how this works, that's +2, stupid. See how this works, visualize what this means, right? This would be a vector that's 5 units in the x direction, so 5 units to the right. But in the y direction, it's only 2 units, so it's 2 units up. Now, remember, when you have components, I put them tail to tip like this because the sum, the thing they add up to, let's change colors, is this. So when I write 5i hat plus 2j hat, it's just another way of saying that red arrow. Notice that red arrow points up and to the right, and it's going to have a length that is going to be bigger than 5, but smaller than 7. Because when you add two vectors that are not collinear, it's not like regular math. But we know how to do that math because we know how right triangles work, and by definition, the x component and the y component are always going to be at 90 degrees. So this will always be a right triangle. So if I know two sides of a right triangle, the way that I find the third is that I remember from elementary school the Pythagorean theorem. A squared plus b squared is equal to c squared. So a and b are 5 and 2. C is the thing that I want. So the hypotenuse of that triangle is going to be the square root of a squared plus b squared. So 5 squared is 25, plus 2 squared is 4, so 25 plus 4 is 29. And the square root of 29 is somewhere between 5 and 6. Can't do that one in my head. If someone had their calculator out, you can tell me. I'm having phone issues. Come on, phone. There we go. 5.38. So I would say that that vector has a magnitude of 5.38 units. Right? That is the size of that red arrow. 5.38 units long. Notice, as I expected, it's a little bit longer than either of the two legs, because the hypotenuse is always the longest side of any triangle. And remember, if I'm describing a vector, I have to talk about both the magnitude, but also the direction. Now, how would I describe the direction? I could say verbally, it's up and to the right. And that's certainly true. If you did it on an exam, I'd give you partial credit for that. But I wouldn't give you full credit, because up and to the right is vague, right? I could have a 5.38 meter long vector this direction, or an equal length pointing this direction, or this direction. All of those are up and to the right, but obviously the directions are slightly different. So to be more specific than up and to the right, I'd have to specify maybe an angle. So I might choose an angle for reference, and I would choose this angle here, because I like to do the angle that it makes with the horizontal. And I could then find that angle, because now I know all the sides of a triangle, and I'm looking for an angle. And conveniently, this is the opposite side. This is the adjacent side. And I remember from SOHCAHTOA that the tangent is the ratio of the opposite to the adjacent side. So the tangent of theta is 2 over 5. And now that's something that I can solve. I will take the inverse tangent of 2/5, which is 21.8 degrees. So, if I were asked what is the magnitude and direction of this vector, I would respond that it has a magnitude of 5.38 units, and it is in a direction up and to the right at an angle of 21.8 degrees above the horizontal, right? The words are every bit as important as the numbers. It is up and to the right at an angle of this above the horizontal. And that's a thing we had to do over and over and over and over again, right? Every time we had to add a bunch of vectors, we're doing this process. And it's important that you be able to go back and forth from describing a vector in terms of magnitude and direction to vector notation. Right? If I say I have a vector that's 5.38 meters long at an angle of 21.8 degrees above the horizontal to the right, that is describing this vector. The other way of describing it is vector notation. So this and this are two different ways of talking about that red arrow. And it's important that you be able to translate from one to the other. If I give you a magnitude and direction, you should be able to break it down like this. If you have one that's already broken down, or if you've broken it down and done some math and you want to go back, you've got to be able to do this process to get back. And again, that's a tool you're going to use over and over and over again in almost every chapter, and certainly well into next semester. So if you learn nothing else this spring, make sure you learn that, because it's important. All right, how are we doing? Does that make sense? Yes, no, maybe. We're all checked out. I find this very frustrating to try to like talk to an empty room. So I really appreciate those of you who respond when I ask questions, because you make my job way easier. So thank you, Amber, for answering questions all semester long. You're spot on. Even if you answer wrongly, it helps me with my cadence and it helps me with my pacing to get a response from a student. So it's super helpful, and I very much appreciate it. So that's what we got up through chapter 3. Now, chapters 4, 5, and 6, that was the stuff that was on exam 2. And those chapters, I always kind of, in my head, I treat them all as like one big old chapter. Because really, all they're doing in those chapters is they're using Newton's laws. And it's super, super important that you guys, you know what Newton's laws are and how they work. So, Newton has 3 laws. What's the first law of motion?
An object tends to stay in motion unless acted. Oh, an object tends to stay at a constant velocity unless acted on and force.
That's exactly right. Yeah, that's important. Both parts of that are important, right? It says objects tend to keep the same velocity, which means they're going to move one speed and in a straight line, because that's what constant velocity means. So they keep constant velocity unless they're acted upon by net force. So if you have an object that's moving, you don't have to push an object to make it move. Once it starts moving, it wants to stay moving. It wants to keep moving in a straight line. It wants to keep moving in a constant direction. And if you want to change its state of motion, if you want to speed it up, if you want to slow it down, if you want to make it turn, you're going to have to exert a net force on that object. Otherwise, it's going to keep doing what it's doing. If the object's at rest, if it's not already moving and you want it to move, the only way that's going to happen is if you exert a net force on it. So that's what the first law is They call it the law of inertia because inertia is just resistance to change, right? It resists changing its velocity. If it's got a velocity, it's happy to keep that velocity. It doesn't want a different velocity, and you've got to exert a force to make that velocity be different. And sometimes that's counterintuitive for students because what happens is sometimes the forces that are acting on things, they're not visible to us. They're not immediately obvious. If I have a pen and I give it a shove, it's going to move, but eventually it stops, right? And I just said that it wants to keep a constant velocity, so it wants to keep moving at one speed in a straight line, and yet when I push it, it doesn't. Why not? Because there's forces on the pen. And as it's sliding across this page, it's experiencing a net force from the friction acting on it. And that friction is causing its velocity to stop being constant, right? So it's got the net force, which is why the velocity does not stay the same. But if I were to take this pen and go into deep, deep interstellar space where it's not rubbing against anything and there is no friction, then there's no air resistance. And if I'm far enough where gravity is negligibly large and I give it a push, this pen is going to keep traveling in a straight line at a constant speed forever. It never wants to stop because nothing is making it stop. So that's the first law of motion. Second law of motion.
The acceleration of an object is directly proportional to the net force and inversely proportional to its mass.
That is absolutely right. So imagine that you wanted to explain this to your little brother, Ryan, and you didn't want to use funky highfalutin math terms. How would you explain it to your little brother? Who may or may not be fictional.
F equals ma.
That's true, but maybe your 5-year-old brother doesn't know what that means either. I want you to really dumb it down.
So
your
the
brother's
net force
5.
equal to the mass and the change in the acceleration.
Yeah, but you still, boy, that still sounds like mathese, right? If I wanted to dumb this down and tell it to a 5-year-old, what I would tell them is that the harder I push something, the more it accelerates. Right? That's what it means, right? The net force is like if you add up all the forces, the bigger that net force is, the more acceleration you're going to get, the more it's going to speed up, slow down, or turn. And the mass part, the fact that it's inversely proportional, means the more mass you got, the more you resist speeding up, slowing down, or turning. That's what it means conceptually. And it's super important that you be able to think about it both ways because, hopefully everybody... this is something everybody knows without being prompted. Again, technically, it's the sum of the forces, not just one force, but all the forces. But what I've often found is that I can put on an exam. In fact, last spring I did exactly this. I put on the exam, the last 3 questions in the first section were, tell me Newton's 3 laws. And I had plenty of students who could answer all 3 laws. They could quote them back to me verbatim. But then, in several other questions, they answered the questions in ways that suggested they didn't know Newton's laws. So it's like they knew what to write when I asked you for the definition, but they didn't know what it means. And so it's important you know both, because ultimately, I don't care if you can quote back the words. I care, do you really internally grok what the concept is about? And all it's saying is, if you add up all the forces and you get some non-zero amount, then that's a net force. That means its velocity is going to change, and it's going to tell you how much its velocity changes by. The bigger the unbalance in the force, the bigger the acceleration you get. The more it's going to speed up or slow down or turn. And the mass part tells me that if I've got a big mass, it takes a whole lot of force to make me accelerate very much. But if I have a tiny mass, then barely any force can cause my velocity to change a whole lot. That's the concept. So, super important. Third law. What's the third law?
Isn't that with the cars? Like if one car is moving at a certain pace and another car is going the same, that they'll both cancel out once they collide with each other?
I thought you had it, but you kind of went off the rails for a second there. So let's clean that up a little bit. Anybody can help her out?
For every force on an object, there is an equal but opposite force on another object.
Awesome. So again, pretend you're explaining that to your 5-year-old little brother, Brittany. What's that look like?
You can say like, if I push something, then whatever I push is gonna push me back the same that I'm pushing it.
That's exactly correct. That's exactly the right idea. If I push something, any force I push on you, you're pushing back on me equally hard, but in the opposite direction. Right? So the two things, for every force, there's an equal but opposite on another object. Right? So what's going to happen is, for that force on the object, that's the push E, the person being pushed, and the other object is the pusher. So what the third law says is that forces happen because two objects are interacting. You can't have a force with just one object. There's got to be a push E and a pusher. And however hard the push E gets pushed, the pusher is being pushed the same amount, but in the opposite direction. Right? And that's going to be useful when you're setting up problems in chapters 4, 5, and 6, because a lot of times you may be doing the free body diagrams on one object, but when you go to do the free body diagram on the pusher object, some of the forces from that first free body diagram are going to show up in that other free body diagram, but they're going to be pointing the other way. So, like, I once did a problem where I had, my dog. Looks like a reindeer, but whatever. And my dog was on a carpet, and she was trying to slow down. So what happened was she's slowing down because of friction from the carpet. So if I do the free body diagram for the dog, is it possible to draw a worse dog than this? I think it might be. Right. The dog was traveling to the right, but the friction was slowing it down. However, that was friction between the dog and the carpet, which means if I did a free body diagram for the carpet, whatever force the carpet put on the dog this way, the dog put on the carpet the other direction. So what was happening is when the dog turns around, the carpet goes sliding in the direction that the dog was originally traveling. And it was an endless source of amusement for me when I had that dog. So that's the third law of motion. If I'm touching you and exerting a force on you, you're exerting that same force back on me. Now, it may be that that's not the only force acting on you. So, for instance, the carpet also is touching the floor, and the floor might exert a force in the other direction, causing the carpet to not move. But if the floor didn't have enough friction with the carpet, then the friction between the carpet and the dog could send the carpet sliding. That's the idea. So those three concepts are super important to grasp, and the next 3 chapters was just us figuring out different ways to implement these things and to figure stuff out. And that was basically it. And so I like to think of it as there being a procedure for basically every Newton's law problem. That is a sheet. There we go. So if I'm doing a Newton's law problem, my procedure is the same every single time. And all that's going to change is sometimes certain steps are going to have some tricks that I can use to implement them. And most of what chapters 5 and 6 were about was, hey, here's a trick you can use in this kind of situation. Here's a trick you can use in this kind of situation. But it's always the same basic process. So the first step in every Newton's law problem is identify what forces you're dealing with. As always, we're going to do a diagram. We call it, in this case, a free body diagram. All right. And that free body diagram is just a simplified sketch of the object with arrows designating each of the forces that are trying to influence the motion of the object. So if I've got a coffee cup sitting on a table, then what's going to happen is there are two forces on that coffee cup. I've got a force from the table pushing it up, and I've got a force of gravity pulling it down. Gravity, of course, is m times g. That's the force that gravity pulls with. And so that would be my free body diagram for that particular problem. So identify your forces, do a free body diagram, identify those forces. Notice when you're identifying forces, a lot of times what I see students do is they'll kind of go through their head and list all the names of all the forces that we've talked about in the semester. And I'll get like weird random forces showing up in their free body diagram that don't belong. Case in point, on the final exam one year, I had a problem where Spider-Man had captured the Rhino and had hung the Rhino outside the police officer's precinct with two webs. And you had to figure out what were the forces in the webs acting on the Rhino. And when they did that, students were like, okay, there's webs, they're like ropes, tension, there's tension. And so they correctly identified there'd be tension in this web and tension in this web. Usually that was pretty quick. They said, oh, there's gravity acting on the Rhino, so mg. And then a lot of them were like, oh, what other forces do we have here? What other force do we talk about? The normal force. Well, the normal force is straight up, and they throw that in there. Now, why is that wrong? Well, the normal force is just the special name that we give for the force of contact between two surfaces. Like this thing I'm calling the force from the table up here, it's an example of the normal force because it's just the force that is from the table, and they call it normal because it's a fancy schmancy math term for perpendicular. The force from the table is perpendicular to the table. So if the table's flat, perpendicular is straight up. That's why it was straight up. But here, the Rhino is being suspended in the air, which means he's not touching the ground. So what's the normal force going to be from? Nothing. So it was incorrect for them to include that force. So if you're trying to identify your forces, one of the best ways that I have found for trying to break this down is to remember that every force has to have a push E and a push R, right? So with one exception, every force that we've talked about this semester has been a contact force. In other words, if I want to exert a force on you, I cannot do it unless I physically touch you. If we're not making contact, I cannot push you, right? And every force we've talked about this semester has been like that, with the simple exception of gravity, right? Gravity is a force where the push E, maybe you, and the push the planet Earth, don't necessarily have to be touching for that force to exist. If I'm taking my pen and lifting it above the air, and I let it go, even though it's not touching the ground, the Earth is pulling it downward. So it's what we call a field force. And the push E and push R don't have to be touching. But everything else, they got to be touching. So one way you can think about it when you're trying to figure out what forces you've got is you should ask yourself, what are the objects touching the thing I'm doing the free body diagram for? So in this problem here, this web was touching him. There's a force from it. This web is touching him. There's a force for it. And we call them T for tension, but you can name them whatever the heck you want. I could have solved this problem calling it W1 and W2. Doesn't matter. The names are irrelevant. And then, of course, gravity is the only force that exerted on him, even though he wasn't touching the object that was doing the pulling, which is Earth. So identify your forces. You know, sometimes I've seen books that suggest, draw a little, like, dotted line around your object, because you know that anything that crosses that dotted line will exert a force on the dude. So if it doesn't cross the dotted line, there's no force from it. And that's a good way of identifying your forces and making sure you don't miss them. So that's the first step of every Newton's Law problem ever. Step 2. Once you've done that, take inventory. Choose coordinates. And take inventory. Now, what I mean by take inventory, well, in this case, what's going to happen is, like, some of your forces are going to be in different directions, and so you're going to choose, an X direction and a Y direction, just like you would in a kinematics problem. And that means you'll assign pluses and minuses based on that. So if I was doing the coffee table example, the normal force is in the Y direction, so it would be positive in the J hat direction, but gravity is downward, so I'd make it negative in the J hat direction. Whereas in this example here, what's going to happen is gravity would still be negative in the J hat direction, but 0 in the I hat direction. But these two tensions, I'd have to break those down into components that we were doing a minute ago. I'd have to have an X component and a Y component for each of them. And I would use Triggs and SOHCAHTOA to do that. So I would break all those forces down into their components. And the reason that's important is because the third step is to do F equals ma, to use Newton's second law. And what's going to happen is, remember, the F in F equals ma is not just any F, it's the sum of those forces, which means I'm adding these vectors together. But when you add vectors, you don't add them like regular numbers, you add them like this. You break them into components, you add the X parts to the X parts, and the Y parts to the Y parts. And in this case, what's going to happen is I may not have numbers for all those things. I may have variables and expressions, and what I'll end up doing is I'll generate some equations. People are always going on about, how do you memorize all these equations? But for Newton's laws, you don't memorize any of the equations. What you do is you figure out the equations based on your drawing, right? If you know how to do the process, you don't memorize a stinking thing. All you got to do is use the process, and it'll spit out whatever equations you need to solve that problem. So by the end of step 3, I'm going to have, one or more equations that I'll have to solve, and some of the things in those equations are going to be known, and some of those things in those equations are going to be variables. And when it comes to step 4, you do the math. Because hopefully, once you've generated that system of equations, there's going to be a solution to that system of equations that you can solve for. And the thing that you're looking for in the problem will be identifiable. So that's the basic process for every single Newton's Law problem we ever do. And all we're ever really doing is tweaking that basic formula to fit a few additional scenarios. That's it. That's the whole deal. So what we'll end up doing is learning tricks for how do I do this in this kind of situation? How do I do this in this kind of situation? What sort of tricks can I use when I break these things down to make my life easier? Let me take a couple minutes. I've run out of these things. I'm going to rinse these off and recycle them. So take 5 minutes, go to the bathroom. I'll be back with a whole slate of things to write on. But you can see some of these were partially wet and they got all smudged. So I need to fix those real quick. And we're back with a brand new clean slate of things to write on. All right, so let's talk about tricks that you have to implement to solve certain kinds of problems. There's all sorts of things that end up being some kind of variation on that basic Newton's Law process. And I try to keep as I guess, comprehensive a list as I can, because part of learning to do this stuff is just sort of learning through experience what kind of tricks work in different situations. The thing that I try to tell my students as much as possible is that, I'm better at solving problems like this, not because I'm smarter than you guys, because I'm not. I am not smarter than you guys. What's different is that I've been doing problems like this for a really long time. And so what happens is, in my brain, I've kind of learned to sort of categorize stuff. And I've learned that when I look at a problem, I notice certain little features that say, aha, this looks like it might be a problem that energy conservation might help me for. Or this looks like a problem on an inclined plane. And I've trained myself that when I see those little things, there's tricks that I can pull out of my bag of tricks that will help me avoid running down dead ends and getting stuck. Whereas you guys don't have as much experience doing this stuff as me. Right? You don't have the background of spending 20 years solving all these stupid problems. And so you haven't learned to categorize those. So whereas I look at a problem and say, man, that looks like it might be an energy conservation problem, you guys are going to look at that problem and be like, well, that's definitely a physics problem. There's probably some physics there. But you don't know how to break that down any further. So I'm trying to give you as much of a heads up as I can on like what features to be on the lookout for that are going to be a signal that certain tricks might help you implement the steps. And probably one of the big ones, one of the ones that happens over and over and over again, is problems on inclined planes. Because man, oh man, do we love in physics to put things on ramps. I love it. So if I have a thing sitting on a ramp and I'm doing it as a Newton's law problem, and notice not every time is it a Newton's law problem. Question 1 on the exam yesterday had a thing on a ramp, but it was an energy conservation problem. And we'll talk about like how you know not to do this trick here for a problem like that here in a minute. It has to do with what kind of stuff I'm asking you for and what kind of information I'm giving you. And even then, we used some of these tricks for that problem, just not all of it. So if I see a thing on an inclined plane and I'm doing Newton's laws on that problem, the trick is that when I go to implement those 4 steps, I'm going to implement part 2 in a very special way. I'm going to do it in a special way that makes life easy for me. Because that's what I want. I want to make the problem be easy. And normally when I'm choosing coordinate systems, I almost always default to make x be to the right and y be up. That's usually my default coordinate system. But if I try choosing that coordinate system for this problem, I'm going to be making it more difficult, possibly impossible to solve. And the reason is because, you know, whatever this box is doing, maybe it's sliding down the ramp, maybe it's getting pushed up the ramp, maybe it's just staying put on the ramp. But if this object's moving on the ramp, what's going to end up happening is if it moves at all, I know what it's going to do. It's going to either slide straight down the ramp or slide straight up the ramp. It's not going to go flying out this way. Taylor, what's your question?
I just wanted to clarify. So for Newton's law, for the second one, if we put F equals ma, is that fine, or do you want us to put the whole?
So very rarely will I ask you a question that just says, "Please regurgitate this formula," right? Mm-hmm. You know, I've done it on in-class exams a couple times, especially like did I do it this semester? I can't remember. I know on last year's final, like in the multiple choice section, the last 3 questions were, what's Newton's first law, what's Newton's second law, what's Newton's third law? Mm-hmm. And on an in-class exam, I might do that. I will definitely not be doing that this semester, because on a take-home exam, that's a stupid question. Because if I say, what is Newton's first law, all you got to do is Google what is Newton's first law and type it in, right? That's you can look in your book and write out. So things that simply involve memorization are not going to be on a take-home final.
Okay.
Instead, I'd ask you questions that if you understood the nature of the laws, you'd be able to answer the question. And if you don't, you wouldn't.
Okay.
Does that make sense?
Yeah.
So yeah, the way you memorize it is kind of up to me, or I mean, up to you. It doesn't really matter. What I'm looking so you understand the concept. And even on an in-class exam, if I said, you know, what is Newton's second law? If you wrote F equals ma, I'd probably give you credit for it, unless the question was more specific. If I said, you know, explain in words to your 5-year-old brother, I'd expect to be a bit more elaborate. But I would have given them credit last semester if they said F equals ma, because that's what it is.
Okay, thank you.
You're welcome. So, doing this problem, this coordinate system sucks. And the reason it sucks is because if this thing moves, let's say that it goes down the ramp, it's going to be moving a little bit in the x direction and a little bit in the y direction. So the acceleration of that object, the displacement of that object, all the qualities of that object are going to have both an x and a y component. And that just means there's more variables for me to have to solve for. That's kind of annoying. However, if I'm clever and I realize that this dude's going to move along the ramp, what I can do is I can choose a better coordinate system. And I can choose to take my coordinate system and just slant it so that the x component is running parallel to the ramp and the y component is running perpendicular to the ramp. The advantage is, if I'm describing the motion of the box using this coordinate system, the x acceleration and the y acceleration, they could both be non-zero, and I don't know either of those two things. So that's two variables to solve for. If, however, I choose this as my coordinate system, it could have an acceleration in the x direction, and that could be anything. I'll have to solve for that. But I know for sure it's not moving at all in the y direction. So I know going in, the y component of the acceleration has to be 0. That means that's one fewer thing I'm going to have to solve for, and the problem will be that much easier. So if I see an inclined plane and I go to do step 2, the trick is slant your coordinate system and make the problem be easier. That's the whole trick. The other thing that you have to be able to do is, once you've slanted that coordinate system, you've got to be able to break your forces down into components. And sometimes that's a little tricky. Because if I'm looking at this box, one of the forces, for instance, is always going to be gravity. Right? Gravity's always going to point straight down. Right? Now, if I was using your regular boring coordinate system, well, gravity would be purely in the y direction, but not in the x direction. So using this coordinate system, I can say that the weight would be 0 I hat minus mg j hat, right? But that's using this coordinate system. If I'm using a slanted coordinate system, what's going to happen is now it's no longer purely in the y direction, because the y direction is diagonal and gravity is not. It's also not purely in the x direction, because it's not completely down the ramp, it's a little bit down the ramp and a little bit inward. So what I have to do is to break that into x and y components. So what I did is I drew 2 lines. I started at the tail of the vector, and I drew one line parallel to the y-axis. The other line is parallel to the x-axis, and that means that by definition, that's going to be a little right triangle. And now I'll break down those components accordingly. And the thing that I recognize is that whatever angle I have here at the bottom of the ramp, it's going to have to be the same as this angle right here at the top of that triangle. And that's going to allow me to break it into components there. So for this coordinate system, the weight would be, for the x component, that's the opposite side. So that'd be mg cosine, sweet, that's stupid, hello, sine of whatever theta is, I hat, and it's down the ramp, which I said down the ramp is positive, so I'm going to leave that as positive. There may be situations where I'd have x be positive up the ramp, and I just put a minus sign there in that case. And then the y component is the adjacent side. That will be mg cosine of theta. And since I chose up and away to be the positive direction, this is down and in, I just slap a minus sign on it. So both of these are correct ways of breaking down the force of gravity, but this is appropriate for this coordinate system, this is appropriate for this coordinate system, and what's going to happen is if I break it down this way, the other parts of the problem are going to be too difficult. So this is a dead end that I wouldn't try. This is going to make my life easier. So that is the trick when I have objects and inclined planes. That's the number one trick that you see in almost every physics exam ever. There's almost always a ramp. Now, what about static equilibrium problems? What do I mean when I say static equilibrium?
The object isn't moving.
Yeah. The object usually means it's stationary or not moving. Now, just to be a little pedantic, you could also have what effectively is a static equilibrium problem, even if the object's moving, provided that it's moving at a constant velocity. Right. So be on the lookout. Even if it's moving, but it's at a velocity that's not changing, so it's going in a straight line and it's not speeding up or slowing down, that's also technically a static equilibrium problem. And the whole trick for static equilibrium problems is when you go to implement step 3, well, you're doing F equals ma, but if you're in static equilibrium, all the a's in every direction have to be 0. That's the trick. So once you recognize that it's static equilibrium, a equals 0 in every direction. And that will make your equations easier to solve. You'll have fewer things to figure out. So,
I'm sorry, what is static equilibrium again?
So static equilibrium is when you have an object that's either stationary, it's not moving at all, or if it's moving with a constant velocity. So, static means stationary usually. Equilibrium means balance. So what's happening is if you're in static equilibrium, the forces, there may be forces acting on it, pulling in every which direction, but all the forces balance out so that you end up with a net force of 0. That's all it means. So all the forces got to add up to 0 because there's no acceleration. That's the trick. So, other than that, it's like any other Newton's law problem. Just do the steps. In chapter 6, we introduced circular motion. Specifically, uniform circular motion. I should say, because that was chapter 6. Now, uniform circular motion just means that I'm moving in a circle, but I'm doing so at a constant speed. But notice, constant speed does not mean the same thing as constant velocity. So if I have a guy who's, say, driving his car, I'm looking at him from above, around a circular track, even if his speedometer says 60 miles an hour the entire way around that track, his speed may be constant, but his velocity is most definitely not constant. Because up here, his velocity is to the right, but halfway around the track, dude is traveling the exact opposite direction. So this velocity definitely changed, and changing velocities means you have an acceleration. So anytime I have an object that's moving in a circle, or even if it's just going around a corner that's like part of a circle, then the trick that I can use is that I know something about the acceleration of the object. The acceleration is going to equal v squared over r in whatever direction points toward the center. So, when I go to break down my forces and do my steps, when I'm choosing my coordinate system, the first thing I'm going to do is I'm going to make sure that I choose a coordinate system where either x or y points towards the center of that circle. Every time. So if I'm doing something with this guy here, I'm going to choose maybe this to be my positive y direction and this to be my positive x direction. So in this case, the y direction would just conveniently point towards the center of the circle. The reason that helps me is because then when I go do my equations, in step 3, I'm going to do F equals ma, which means I'm going to get one equation in the x direction and another equation in the y direction. However, the acceleration in the y direction is going to have to equal that. So I put that in, and that's the trick. So that's what I do with circular motion. That's the whole way of breaking that down. There's a couple other places. Let's talk about contact forces. That's another one that I'm a big fan of. Right. So when I mean contact forces, maybe I should put parentheses connected objects. two or more objects that are all interacting with each other at the same time. We did an example in class where I had a box and another box, and what was happening is the two boxes were touching, and I walked up and I'm pushing the box on the left to the right with some amount of force. And what's going to happen is when I push that box to the left, that box is going to try to accelerate to the right. But it can't accelerate to the right without also pushing box number 2 to the right. And what's going to happen is these two objects, they're going to end up moving together, right? Whatever motion the first object has, this object's going to have to match that motion, because otherwise object 1 would plow right through the first object. That can't happen. So the trick for this kind of problem is that when I go to implement step 1, first, I'm going to do a free body diagram for both objects individually, right? So if I'm doing this problem over here, and I do object 1, there's going to be several forces acting on object 1. There's going to be a force from the floor, pushing it upward. There's going to be gravity, pushing it downward. There's me, I'll call that P for push, pushing it to the right. But it's also touching object 2. Because it's touching object 2, there's going to be a force from object 2. And it's going to push it to the left. So I'm going to call that F12. Right? You can call it whatever you want. But those are the 4 things that are touching object 1. There's me, the floor, gravity, and object 2. So there's 4 forces on it. When I go to do the free body diagram for object 2, however, what's going to happen is it's touching the floor, so I'll give it a normal force. It might be different from that one, so I'll call this N2 and the other one N1. It's got gravity pulling on it, just like anything else, so M2G. However, the force of me pushing, I'm not touching object 2. I'm touching object 1, which means I can't be exerting a force on object 2, so there is no equivalent to that force on this guy. However, Newton's third law says that if object 2 is pushing object 1 this hard to the left, that object 1 must be pushing object 2 this hard to the right. So I'll have an equal but opposite force on that. So the trick with these connected object problems is, first, when you're doing the free body diagram, break it down and do free body diagrams for each object separately. Then, when you get down to step 3, and you're doing F equals ma, remember, these two objects are connected. If object 1 accelerates to the right at, say, 2 meters per second squared, if object 2 doesn't match it, then object 1 is going to plow right through the middle of it. That can't happen. Which means I know that at least in one direction, the accelerations have to be the same. So they're going to have the same accelerations. So if I were solving this problem all the way through, and we've done it before, we did it in class, then what would happen is I'd have a total of 4 equations. I'd have one in the x direction for object 1, another in the y direction for object 1, another in the x direction for object 2, and another in the y direction for object 2. So 4 equations. However, if object 1 is moving to the right, it has some acceleration in the x direction. Object 2 has to have the same acceleration. So the x component of the acceleration for this box must be the same as the x component of the acceleration for that box. And by putting that in, I'll be able to solve my problem. Super easy. Now, a couple other things that you're going to have to wrap your head around in chapters 4, 5, and 6, where there were certain forces that had special rules, right? Not very many of them. They showed up in chapter 5 for the first time. But in chapter 5, we introduced the concept of air resistance, or viscous drag. Right? What was the drag force? Well, there was a formula for that. If you're traveling at relatively high speeds, the drag force was given by CA rho V squared. So, people talk about, memorizing formulas. That's a formula that I'd probably have to know. Or at least I'd have to know what all the various things in that represent. So D is the drag force. It's the force of the air pushing on you as you get it out of the way and you move. So it depends on something called C, which is the coefficient of drag. A, the cross-sectional area. Rho, the density of air. And then V is how fast you're trying to move. You just got to know that. And again, this is one of those places where if I'm looking at a homework problem and it's got this thing moving and they go out of their way to tell me the density of air in the problem, that's kind of a what? Because usually we ignore air resistance because it's complicated. And I'm only going to tell you this stuff if I want you to take it into account. So here, just know what all this stuff means. The tricky part is, this is obviously a constant you could look up. It's probably going to be given in your problem. V is how fast you're traveling at a particular moment. Notice, the faster you're traveling, the bigger the drag force. That's why if I'm just walking back and forth, I don't even feel the air resistance. It's so wimpy, I don't even notice it. But if I'm driving my car at 80 miles an hour down the freeway, which I totally would never do because that's illegal, but if I were to do that and stick my hand out the window, I would totally feel the air. Why? Because my velocity is so large that I'm having to push the air out of my way for my hand to move through it, and that would be a noticeable force. So, especially at low speeds, we usually ignore this, but at high speeds, it starts to matter. The tricky part here, like the coefficient of drag, it depends on the shape of the object. It's a number. The way we figure them out to begin with is we put things in a wind tunnel, and we just measure it. If this was an exam problem or a homework problem, I would tell you what the coefficient of drag was, or that would be the thing you were solving for. But there's no way to determine it other than just experimentally. The tricky part here is A, and that's called the cross-sectional area. And the reason the cross-sectional area is important is because it's the area of the object that is seen by the air as you move through it. So imagine I'm doing this pen, right? This pen is moving through the air. I could move it two different ways. If I move it this way, maybe I'm moving it through the air like this, then as the air sees the thing coming, it's going to see a profile that looks like this. It's going to be long and skinny, right? So the cross-sectional area would be just this length times this length, right? That's area. However, what if I take the pen and I orient it like so, and I shoot it forward like this? Well, what's going to happen is the air only sees the tip of the pen, right? The cross-sectional area would be the area of this shape right here, which would be considerably less, right? If this was a circular pen, I'd do pi r squared or whatever. So the area you see depends on your orientation relative to the air. If I had this pen kind of angled like this and I moved it like that through the air, then what's going to happen is, so you can kind of see like this is the area when I go full on, and notice how when I tilt it, in your view, you see how this shape looks like it's smaller? Because the air is seeing a smaller amount of area. So as I change the orientation, the area is getting smaller and smaller and smaller until it goes to this. And then it would get bigger as I keep tilting it. Does that make sense? You guys follow that? So
Yes.
yeah, that's it. That's the whole deal. So that's the trick. When you're incorporating that force, you just have to know how to do that. Super easy. The other force, which is related to the drag force, is the frictional force. You should definitely know how to deal with the force of friction. And all you really need to know for the force of friction is basically two things. One is that friction obeys certain rules. The amount of force you get from friction is going to be given by the coefficient of friction times the normal force that you have with whatever surface is causing the friction. So if I had my coffee mug and I'm dragging it across the table to the right, the frictional force would be to the left, right? It's going to always oppose whatever direction I try to slide it. So first you have to be able to figure out the direction of your friction. And then once you know the direction of your friction and you put that into your free body diagram with your other forces, then the thing you have to do is realize that since F depends on the normal force, and the normal the friction is always going to be in one direction, and the normal force is always going to be in the other direction, you're going to end up with equations in X and Y, and you'll have to use both of them in tandem to solve the problem. So my coffee cup was sliding across the counter, basically just coasting to a stop. This would be my free body diagram. And my equations would be in the X direction, I have one force, so F, or UN, equals MA in the X direction. And my Y direction forces would be N minus MG is MA in the Y direction. And then I'd pause for a second and I'd ask myself, what do I know about the acceleration in the Y direction? Well, the coffee mug is definitely not moving up and down at all. So I can make that be 0. And so I have two equations. And if I was, say, trying to solve for the acceleration, I'd notice that I don't know n in that equation up here, but n also appears in that equation down here. So I'd solve this equation for n and then plug it into the other equation and eliminate it. So the thing about friction is that you almost always have to use the x and the y direction equations together to solve for whatever it is you're trying to solve for. And that's the whole trick. How are we doing? So far, so good?
Yeah.
Yes.
Are there any questions about chapters 4, 5, and 6 that you feel like you need to bone up on before I zoom past other stuff here?
Everything that's already pre-recorded is on Canvas, right?
It'll eventually be. What happens usually is the videos get processed for a while by Zoom, and they'll show up in the cloud sometime after we're done. Usually it's maybe an hour or so. I always get an email notification when it goes up. And then I try to migrate them after a few days to YouTube so that they don't use up all the space on the Zoom cloud storage. I haven't done that for a while, so I need to probably do some of those. Once I migrate them to YouTube, there's that previous videos tab that I made an announcement about a while back, and you'll see links to them there. So yeah, everything that's been recorded will show up eventually. It just depends on where you're looking at it. So originally it'll be on the Zoom tab if you look at the previous recordings. Then later it'll migrate to YouTube. But one place or the other should be able to find it. All right. Well, that's chapters 4, 5, and 6, kind of in super Cliff Notes form. And those are the big ideas. But remember, we could run through these ideas really, really quickly. But the real test is going to be, can you do this yourself? And that's only going to come from practice. So practice, get good at breaking them down. But remember, every Newton's Law problem, same freaking 4 steps. Worst case scenario, do the steps as well as you can. Know what steps you need to be doing, right? You can get a lot of partial credit just by knowing, hey, I got to do a free body diagram. Oh, yeah, let's draw some forces. I got to choose some coordinates. Here's the coordinates I'm going to pick. Taking inventory of what you got, break it into components, get some equations. It's if you follow the procedure, these problems are all easy. Next chapter is chapter 7, and chapter 7 is where things change a little bit. Because at that point, we stop talking about forces and acceleration, and instead we start talking about work and energy. So the two big ideas that chapter puts forth are the concept of work and the concept of conservation of energy. That's the big idea. So what the heck is work?
Work equals FD cosine theta?
Yeah. Work is the exertion of a force through a distance, which mathematically is the dot product of F and D. It's the force times the distance times the cosine of the angle between them. So F, D, cosine theta. And that's important because, like, in casual conversation, if you say, boy, oh boy, that was a whole lot of hard work, you know, when you're describing something you've done, in physics, that may or may not have been work, right? If I said, hey, here's my bowling ball. It weighs 16 pounds. I want you to hold it. And I come back 20 minutes later and you're still holding that bowling ball. You know, you might be tired, right? You might think, man, it was a lot of hard work holding that stupid bowling ball. But in fact, you will have done zero work. In a scientific sense, in a physical sense, you will have done zero work. Why is that? Because you're holding the ball, but you're not going anywhere. There's a force you're exerting to hold it, but you're not traveling across any distance. So holding my bowling ball for half an hour, zero work. Now, what if I said, hey, take that bowling ball and I'd like you to bring it over here. So you're holding the bowling ball and you walk across the room. Did you do any work?
Yes, because you walked across the room.
Almost, but let's think this through for a second. Here's the bowling ball and I'm holding it. Now, as you walk, what direction are you pushing to hold that bowling ball? Let's assume you're walking at a constant speed. Like, what direction is the force that you're exerting on that bowling ball?
Upward?
Yeah, I gotta push upward. So this is the force you're pushing with. And I'm moving from here to later on, you're over there. So I'm crossing that distance. So there's definitely a distance. There's definitely a force. But the problem is this cosine of theta part. Because that cosine of theta part is the angle between F and D. And so even if I had you hold my bowling ball and walk at constant speed for a mile, you might be after the end of that mile feeling like, man, I'm really tired. But you will have done zero work because the cosine of the 90 degrees between those two forces is zero. You did zero work even though it feels like you're tired. Now, if I said, here, take my bowling ball and take it up the stairs, well, now what's going to happen is the distance that I'm traveling is this way, the force that I'm exerting is this way, and what's going to happen is the work that I do going up the stairs will be non-zero. And the way to think about it is that this force has a component. Part of it is in the same direction as D, and part of it is perpendicular to D, and only the part that's the same direction as D matters. So the reason that cosine of theta is there is because we only care about the part of the force that's the same direction as D, or the part of D that's in the same direction as the force. So conceptually, like if I'm pushing upward, D is a little bit up, that part of the distance matters, but it's also a little bit sideways. The sideways part makes no difference. So you got to be able to calculate the work being done by force. And sometimes that's tricky. If I'm Spider-Man and I'm swinging from point A to point B, and I want to think about how much work is being done by that web. Well, what's tricky about this problem is that the distance that Spidey is traveling keeps changing, right? Because he's traveling with a velocity that is always perpendicular at all points to that little dotted line, right? So I can think about D having different distances or different directions along the path. But when Spidey is here, he's traveling this direction, the web is pulling towards the center of the circle. That's a 90-degree angle. Right then, it's not doing any work. When Spidey is here, he's traveling this direction. The web is toward the center of that circle. No work. Right here, when he's at the bottom, the web pulls straight up. No work. So what's going to happen is because the direction he's traveling is always tangential to that circle, And because the web is always radial to that circle, the whole way down that angle stays 90. Which means at no point does any work get done. In order for that web to do work, what would have to happen?
Can you repeat the question?
So if Spider-Man is swinging from up high to down low, and he's swinging on his web, the entire time he's moving perpendicular to the force of the web. So he's not doing any work at all on that swing. So if I wanted the web to do some work, what would have to happen as Spider-Man swung?
Would you have to figure out the momentum?
No. I mean, it's not. I have to figure. It's not something I need to figure out. What I mean by that is, what would have to physically occur?
Would he have to stop and keep going? Like stop each time in order to do a certain amount of work?
No, because that would just mean if he did like little tiny baby swings and stopped from time to time, what would happen is the work done during the first baby swing would have been 0. The second baby swing would have been 0. It still would have been 0. It just would have been breaking it up into more pieces. So not that. Instead, what would have to happen is the distance he travels would have to have some component in the same direction as the web. But for that to happen, if you're like hanging on a string, for me to have a motion in the same direction as the string would have to either stretch or compress. So if his webs were stretchy, and as he swung, they were getting longer and longer and longer, then that would mean that there'd be some part of his distance traveled that would be in the radial direction. And that would mean the web was doing some work. But as long as the web stays the same length the whole time, he's locked in and has to move along a circular path. So his motion is only going to ever be perpendicular to that radial direction. Nothing done. So, you got to know the concept of work. The other big key concept is the concept of conservation of energy. And almost every problem in Chapter 7 can be solved using the same basic process, right? You've got something moving around, and you're trying to figure out something, and you know that maybe you're under the influence of nothing but conservative forces. And if that's true, the following statement ought to be correct. This is the total mechanical energy that I start with. This is the total mechanical energy that I finish with. So what's going to happen is, if there's no non-conservative forces, I can make that statement. Now, what the heck is a non-conservative force?
The question.
So I said that this statement is only true if all the forces are conservative and there's no non-conservative forces. So if I'm going to know whether or not that's true, I need to know what the difference is between a conservative force and a non-conservative force. So what the heck is a non-conservative force? What the heck is a conservative force? How do I tell them apart?
The work depends on the path you take, like non-zero work over a closed path.
That's right. For a non-conservative force, the amount of work that it takes depends on what path you take from point A to point B. If you take a different route to get there, you might do a different amount of work. That's true for non-conservative forces. For a conservative force, what's going to happen is, anytime you go from someplace and you come back to where you started, you will always end up with zero work. And that means that to go from point A to point B, the work's always got to be the same, because if I go from here to here, like from here to here, and I do 10 joules of work, then if I go back to where I started, it better come up with negative 10 joules of work. And it can't matter whether I go straight back down the way I came or if I go over and down. The route that I take can't make a difference if I'm requiring that all the work over a closed path always be zero. So non-conservative forces, they're going to have work that depends on the path. But conservative forces are going to do work in a really predictable way. It's always going to be the same from point A to point B, regardless of how I get from point A to point B. That's the big concept. And if I only have conservative forces, this is true. If I have some non-conservative forces, then I might start with a different amount of energy than I finish with. However, the amount that these things are different by is going to equal however much work got done by those non-conservative forces, because non-conservative forces do work in an unpredictable way. So all I got to do to make it correct again is to add in however much work those non-conservative forces are going to do. Does that make sense? And that was the key for like the very first problem of the exam the other day. You had a thing like this, you had a box, and you wanted to figure out how high on the other side the other box went. Funny thing is, I actually found several people who had posted this one to Chegg, and even the Chegg guy got it wrong a little bit. So the reason is because in the problem, there was friction the whole way over, but the solution I saw from the guy on Chegg, he assumed there was only friction on the bottom part. And that's why if you you used his solution, you got the wrong answer. There was actually friction the whole way down, the whole way over, and the whole way up, and that made your answer a bit more complicated. Had you done that on your own, I would have given you probably 19 out of 20 points if you'd only done it on the bottom, but in the question, it doesn't specify where the friction happens. It happens the whole way. But that's how you do it, right? You know, this is true. I'm going to have to figure out how much work gets done as I slide along the thing, and that requires a little bit of savvy. It's important that you be able to recognize what K and what U represent. K is the kinetic energy, 1/2 mv squared. U is the potential energy, the energy stored by a conservative force. And every conservative force is going to have its own potential energy formula. For gravity, the potential energy is mgh. For some problems, you might have springs, and the potential energy is 1/2 kx squared, and that's it. And so anytime you're solving an energy conservation problem, you're starting from this basic skeleton, and you're filling in the blanks to fit your problem. So on a problem like this, if my object starts out at rest, that means that originally 1/2 mv squared would be 0 because I'm starting off at a velocity of 0. So for that kind of problem, I would make this be 0. If I had a problem where the object was moving at the beginning, then this would just be 1/2 m times whatever that v was squared. I'd plug that in. Right? U is going to be the potential energy. If there's a spring in the problem, I'd use this, but if there's no springs, it's all mgh all the time. And obviously here I'm at mg times whatever this h is, and here I'll be at mt times some different h, and I'd be solving for that other h. So you fill in the blanks, you do the algebra, you solve the problem. That's the big concept for like 9 out of 10 problems in chapter 7. And all that's going to ever change is how do I implement this to fit my particular situation. So that was chapter 8 or 7 in a nutshell. Chapter 8. What's the big deal with chapter 8? So chapter 8, we learned another concept. That's the concept of momentum. Momentum, which for historical reasons is P, was m times v, mass times velocity. Now, what makes that tricky is that velocity is vector. I'm multiplying it by a non-vector, so my result is also a vector. So anytime I'm dealing with P, I got to remember how to break things into components, do the X parts and the Y parts, and that can make some of those problems tricky. It also means that I have to pay attention to direction. If I have something with a velocity to the right and something else with a velocity to the left, one of them is going to have positive momentum, the other will have to have negative momentum. And I'll settle which one is which when I choose my coordinate system. And the big concept for most problems in the momentum chapter is that momentum is conserved. If I've got a bunch of objects, if I add up the momentum of all the objects to start with, as long as the objects are not undergoing any external forces, meaning if I have, let's say, 10 objects, those objects can, if they exert forces on each other, but there's no 11th object out there that's also affecting them, then all the momentum of those 10 objects has to be conserved. Whatever total momentum I had before will be the same as the momentum I have after. And that's this. Boom. I have, let's say, 2 objects in one dimension, then it'll be the mass of the first object times the starting velocity of the first object plus the mass of the second object times the starting velocity of the second object. If there's more objects, I'll just keep adding more things. And then at the end, they all might have different velocities. But if I add up all the momentums of the objects before and all the momentums of the object after, they better be the same. And hopefully in the problem, you were given enough information to plug in for the things you do know and only have one thing missing. That's the trick. The good thing about momentum is that momentum is going to be conserved in all collisions all the time. And 9 times out of 10, if you see 2 things colliding with each other, it's a momentum problem. That's kind of how you tell. And so the process of that collision, the momentum will be conserved. But there's different kinds of collisions, right? We divide collisions into categories of elastic and inelastic. Now, when I say that a collision is elastic, what I mean is that in addition to this being true, because this will always be true, I also have an extra arrow in my quiver, an extra piece of information that might help me fill in a blank. And that's that the energy before is the same as the energy after. The energy is conserved. So if I have an elastic collision, this is true for all the objects, but also the energy is conserved. So 1/2 m1 v1 initial squared plus 1/2 m2 v2 initial squared plus 1/2 m3 v3 initial squared. That would be my starting kinetic energy. That would have to equal my final kinetic energy. And that gives me an extra equation that might help me fill in a blank. If I have an object or a collision that's inelastic, then I'm going to have a different amount of energy before the crash than I have after the crash. So the energy is not conserved. Because I can't count on the energy being conserved in an inelastic collision, I have less information with which to construct equations. So in order for me to give you a problem that's solvable, I might have to give you more information. If I had 3 objects bouncing off of each other, and I wanted you to be able to solve it, and I didn't tell you that it was elastic, so that it might be inelastic, in order for you to solve that problem, I can only have one thing in the equation you don't know. So if I told you all the masses and all the starting velocities, and 2 out of 3 of those ending velocities you could solve for the third one, just knowing momentum is conserved. But if I told you these things are colliding and it's elastic on top of that, elastic, not inelastic, then what would happen is I know this is true, plus I'd have another equation from energy conservation, which means I'd have 2 equations. I could have up to 2 unknowns. So I can give you the same problem and say, hey, here's 3 objects, here's all the masses, here's all the starting velocities, V1 final is blah, 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 and then you could use those 2 equations to solve for the other 2 missing pieces. So I could give you less information in the problem if you knew going in that it was elastic. Now, obviously, a 3-particle problem is algebraically a pain. You could do them. But we did in class the special case of a 1-dimensional elastic collision between 2 objects. And what happened was we started with the momentum conservation equation, except, of course, there wasn't any object 3 to speak of. We had an elastic collision, so that implied that this was true, right? The starting kinetic energy of the first guy plus the starting kinetic energy of the second guy had to be the same as the ending kinetic energy of the first guy plus the ending kinetic energy of the second guy, right? We started out with both of those equations at the same time. We did a whole bunch of hairy, disgusting algebra, and we ended up with that special case of solving that V1 final was it M1 minus M2, yada, yada, yada. Yeah, that equation. We derived it in class. It shows up in every textbook ever. If I wanted to find the final velocity of object 2, it's the same equation, except I swap all the 1s and all the 2s. And I could use that as long as I know going in that all the motion is along a straight line, and on top of that, I have to know going in it's elastic. If I'm not sure if it's elastic, can't use these equations. I just got to use this and hope that the problem gave me enough information to fill in all the blanks. The last sort of special case was the case of things that are perfectly inelastic. Perfectly inelastic collisions are obviously inelastic, but saying something is inelastic is kind of vague. Right? If I was elastic and I started with 100 joules of energy, I'd finish with 100 joules of energy. My starting energy and beginning energy have to be the same. But if I'm inelastic, maybe I start with 100 joules and I end up with 75. Or maybe I start with 100 joules and I end up with 50. Or maybe I start with 100 joules and I end up with 0. Any of those are possible, right? Inelastic covers a whole lot of ground. Perfectly inelastic collisions lose the most energy you could ever lose. Now, when I say the most possible energy, I don't necessarily mean 100% of the energy, because I still have to conserve momentum. And so if I have two objects that collide, and before I have 100 joules worth of energy, but I have a non-zero amount of momentum for both of those objects, then after the collision, I still better have a non-zero velocity. So they might still have some energy, but no other possible way of colliding could give you less energy than a perfectly inelastic collision. And the cool thing about perfectly inelastic collisions is that you're always going to know them when you see them, because when they occur, the two objects, they collide together and they stick. And after the collision, they're going to both be moving with the same velocity. So they will always stick together. And that makes them super easy to spot. Right? So if I was doing a one-dimensional problem with two objects, one and the other, that's initial, not final, then after the collision, they're stuck together. I'll treat them like one big object. The mass of that one big object would just be the total mass, and they've only got one velocity because they're stuck together, which you'll notice this is going to be easier for me to solve than this, because if I told you my starting velocities, here I have two final velocities to solve for. They could be different. They could be anything. If it's perfectly inelastic, though, after the collision, there's only one thing to solve for. It makes those problems easier. So I don't need additional information to solve the problem. So those are super, super easy to spot. If you have a problem and you don't know whether it's elastic or not, the trick is to use momentum conservation, this concept, solve the problem, and then after you're done, go back and compare, is the energy before the same as the energy after? If the answer is yes, it was elastic. If the answer is no, it was inelastic, right? So if they bounce apart, it could go either way. You don't know whether it's elastic or inelastic. You'll have to do the math to figure it out. If they stick together, you don't even have to do the math to know that it was inelastic, because it's perfectly inelastic. And that was the other big concept. Now, we can make these problems more difficult by doing them in 2 dimensions, but all you're really doing when you do it in 2 dimensions, if this is you coming in here and you're flying apart this way and you're flying apart this way, all you got to do is when you're breaking down your momentums, you break them down into x and y parts. And so what's going to happen is when you say that momentum is conserved, right? This is saying if I add up all the momentum before, it equals to what I get when I add up all the momentum after. But since I'm adding up vectors, you have to add them like vectors, which means when I'm adding up all the vectors, I got to do it separately. I got to do all the momentum before in the x direction, and that should equal all the momentum after in the x direction. And then as a separate equation, I'll do the sum of the momentum before in the y direction and the sum of the momentum before or after in the y direction. So in a two-dimensional problem, I won't just have one equation like this. I'm going to have at least two. One for the x direction and one for the y direction. And when I go to solve it, I might have to do algebra that uses variables from one equation in the other to figure stuff out. But that becomes an algebra problem rather than a physics problem. All right, so I know that was lightning fast, but this stuff should be pretty fresh on your mind since you literally just got tested over it yesterday. That's why I'm kind of zigging through it pretty quick. Any questions about momentum? Do you guys feel like you sort of get the big picture concepts? Because this is the big picture concepts.
Kinda, yeah.
The big thing is you just got to practice, right? Some of these problems are algebraically challenging, and you got to be able to sit down and chug through them without losing track of stuff. That's the important part. Then the last little bit of review is torque. I got 10 minutes. I can at least talk about torque in general in 10 minutes. So torque is the rotational analog of a force. Torque is a force that makes an object want to spin, right? But when it comes to rotational motion, the amount of torque you generate depends on where you apply the force. If I've got my little pen here and I have it free to pivot around this finger, if I push at that location, you'll notice I'm making it move translationally, but it's not rotating. If, however, I have it pivot around this point and I push here, all I'm doing is rotating the pen, not moving it translationally. So depending on where I apply the force, I could get translational motion or rotational motion. And that's what torque is all about. Torque is going to depend on where the force is applied to determine whether or not it makes the thing want to rotate or not. And the way we defined torque is we said that torque was the Greek letter tau, and it was R cross F. Notice, unlike work, which was also a force times a distance, here we're using the cross as opposed to the dot to say that when I multiply these two things together, my answer is another vector. When I multiply these two things together, my answer has no arrow, it's not a vector. So it's two different ways of multiplying together vectors. And that's important because if I want to know just how big the torque is, the magnitude of the torque, it's going to be the magnitude of R times the magnitude of F times the sine of the angle between R and F. And the reason that matters is because if I've got this thing pivoting around a point here, if I push perpendicular to the stick, I generate torque. I make it want to rotate. If, however, I grab it and I pull parallel to the stick, I make it want to move this way, but I don't make it want to rotate. So the direction of the force makes a difference. If I'm grabbing and pulling it with a force perpendicular to the stick, F points this way, R points from the pivot to where I'm touching it, so R points that way. So it would be however big this force is times however big this distance is times the sine of the angle between those two things, which is 90, and the sine of 90 is 1. So pushing here, I get all kinds of torque. If, however, I pull this way, and R is this way, no matter how much I pull, the angle between these two things is 0. The sine of 0 is 0. And as a consequence, I don't get any torque. If I were to push at some funky diagonal, pull diagonally this way, I'll get torque, but not as much. Because now the angle between this and this is that angle there, which is non-zero. I get a number between 0 and 1. So that was the big concept that we introduced in Chapter 9, was this concept of torque. And it mattered not just how hard you pulled, but also where you pulled. And in terms of the stuff in Chapter 9, all of the things that we did in that chapter were static equilibrium problems. Right? In a static equilibrium problem, you've got an object that's stationary. It's not going anywhere. Now, when we did static equilibrium back in Chapter 4, we weren't worried about making things rotate. We were basically assuming that all the forces acted at the center of mass of the object, and as a consequence, generated 0 torque. But in Chapter 9, we started worrying about where the forces were. And that would allow things to rotate. So if I've got a seesaw, and I'm pulling this end down with a force m1g, and this force down with a force m2g, and the fulcrum here in the middle is pushing upward with a force that I'll call n. What's going to happen is, if this little seesaw is balanced, it means that 2 conditions have to be met. One is, from Chapter 4, the seesaw can't be moving up, down, left, or right, which means the sum of the forces has to be 0. That's just the old static equilibrium definition we had back in Chapter 4. But in addition to that, it can't be rotating either. And that means that if I add up all the torques, I got to make that be 0 as well. So every problem in Chapter 9 is basically just make both of these conditions be true and be able to set up the equations you need to solve the problem. And again, we're going to get them the same way we always do. If I'm doing the sum of the forces, right, I would take inventory of the problem the same way I would in a Chapter 4 question. You'll notice here I have forces up and down, but not left and right, so all of them are in the j-hat direction. And when I add up all the forces in the j-hat direction, I'm going to have a positive one up minus these 2 negative ones. So that's the sum of the forces, and the sum of the forces was 0. Boom, there's an equation. When I go and I do the torque, well, torque is RF sine theta. I'd have to pick a place to be my axis, and I could pick any place I want. Maybe I pick one end, maybe I pick the middle. I'm going to pick the middle for this one, because I don't really care about n. And what would happen is I would have a torque from each of these 2 forces here, but none from n, because the torque from this guy would do RF sine theta. Well, for n, the R would be 0, because it's happening right there at that spot. If R is 0, the whole thing is 0. So no torque from this guy. I'll get torque from this guy. For this one, R would be however far that is. F would be this. The angle would be 90 degrees, so I'd have R times M1G times the sine of 90. Now, I have to choose a coordinate system, and traditionally, things that go counterclockwise are positive, and things that go clockwise are considered negative. In math, that's how they usually do it. So in this case here, this guy would make it want to rotate counterclockwise. I'll slap a minus sign on it. Meanwhile, this guy over here makes it want to rotate clockwise. That's the opposite direction. So that's positive. It'll be this distance times this force times the sine of still 90. And that's got to equal 0. And once I have those equations, I solve for whatever information I don't already have. Super easy. So, that's kind of chapter 9 in a nutshell. And all it ever really changes is like, how do I break down the torques for all those objects? All right, I've been talking to you guys for like 3 hours. I'm tired. Ranting makes me tired. So I'll see you guys tomorrow. That's what we got. Please study hard.
Some more review tomorrow.
I'm sorry?
Are we going to do some more review tomorrow?
That's the plan. My plan is hopefully to have the exams back, and we'll go over that exam, which is why I kind of alluded to it a couple places here, but it didn't solve them in complete specificity. I was just trying to sort of say, hey, this is where that showed up in the chapter. But yeah, I'll probably hand those back. We'll do some more review tomorrow. I typically will do a review session like we were doing in class meetings. I'll do a review session during the reading day. So we'll schedule that tomorrow and figure out when and if that's going to happen. But that's it for me. See you later.
Bye.
Thank you.
Bye.
See you. Thank you.
Thank you, guys.